This lesson is about simple linear equations and linear functions. We're going to be looking at solving these linear equations, and we're going to be looking at how we can understand the solution of these linear equations using mapping diagrams that visualize linear functions. We begin by looking at linear equations, and in particular, a rather simple linear equation, 5x minus 7 equals 8. We'd like to solve this equation, which means find an x that will make the equation true. That is, the number on the left-hand side, 5x minus 7, should be equal to the number on the right-hand side, 8. We will follow the usual algebraic steps to solve this equation. To begin with, add 7 to both numbers, the number 5x minus 7 and the number 8. Adding 7 to these two numbers will give us 5x for 5x minus 7 plus 7, and 15 for 8 plus 7. Since we're looking for an x where 5x minus 7 will equal 8, if we add 7, we get numbers 5x and 15, which should also be equal. We divide these numbers, 5x and 15, by 5, or multiply them by 1/5. And when we do that, we will have equal numbers if our original 5x minus 7 was equal to 8. 1/5 of 5x gives us x. 1/5 of 15 gives me 3. And so we've arrived at the possible solution for our equation, x should equal 3. We check this by computing 5x minus 7 when x is 3. That's 5 times 3 minus 7, which gives us 15 minus 7, which is 8. So we have checked that when x is 3, 5x minus 7 does equal 8. Now let's start understanding this linear equations by relating the linear equation to linear functions. So we're going to look now at the right-hand side of our screen, and we notice that the computations to check whether 5x minus 7 did have 3 as a solution, that we took the number 3 and replaced that for the x in 5x minus 7. Well, taking a number and replacing it in the expression 5x minus 7 and computing the value is another way to describe the function that we'll call f. And the function f at the number x is computed by taking the number x, multiplying by 5, and subtracting 7. This linear function can also be understood as a composition. First, we use the function m, which when computed on x gives us 5 times x, and we follow that by the function s of x, which takes the number x and subtracts 7. Our function f is the composition of this function. First do m to x, that is, find 5x, and then take the number m of x and subtract 7. So we get 5x minus 7 is the composition of s with the function m. So first do m, then do s. Here's a table for a number of values starting with 4 and going down to 0. We have 4, which multiplied by 5 gives us 20, and then subtracting 7 gives us 13. 4 gives us 20, then 13. Similarly, 3 gives us 15, and then 15 gives us 8. 2 gives us 10, and 10 gives us 3. 1 gives us 5, and 5 gives us negative 2. And 0 gives us 0, and subtracting 7, we get negative 7. So this table gives us a sampling of the values of the function at numbers from 4 down to 0. If we look at the table and ask the question, when does f of x equals 8? We can see that the number 8 did appear here as a result of our function. We do see that f of x, 5x minus 7, was equal to 8, and that happened here when x equaled 3. So we have our solution from the table. Now we want to visualize this. We're going to take the information in this table and transfer it to a mapping diagram. In this mapping diagram, we have three axes. The first axis will be keeping track of our variable x. The second axis keeps track of the value of m, so I'll put an m in between that axis and the second axis. And the third axis is keeping track of the value of our function, which is found by taking the value of m of x, which is on our second axis, and applying s to it. So I'll put an s over the space between the second and third axis. And now we'll see how this diagram visualizes the function by looking at how the arrows are located. We'll look at what happens here at 1. So when x is 1, the value of m of 1, which we see from our table is 5, we have an arrow from 1 to the number 5. From the number 5, we now apply the function s. And so from the number 5, we have an arrow going to the number -2. We're going to visualize that by drawing an arrow down here, and we'll have to go a little bit lower in the scale here to put in the number -2. Similarly, m applied to 2 gave us the number 10. S applied to 10 gave us the number 3. We subtracted 7 from 10. We got the number 3. We can see that the number 3, when m was applied, gave us the number 15. That was m of 3. And then subtracting 7 from 15 gave us the number 8. In this mapping diagram, the first axis has the values of x, and sampling from that, giving us arrows pointing to the values of m of x, and then we have arrows going from the values of m of x to the values of s of m of x, which are the values of our function f of x, 5x minus 7. So we find 5x, and then we subtract 7 in this mapping diagram. How do we understand our equation solution from the mapping diagram? We wanted to find out when f of x was equal to 8. We looked at the number 8 on our mapping diagram, and we traced back to find out which x gave us that number 8 as the value of the function. We trace back first along the s arrow, so we're reversing the s and finding that the number 8 came from the number 15. Then we trace back from the 15 to find out which x gave us m of x equal to 15. And so we come back along the arrow and find the number 3, tracing back from the 8 to the value of x that gave us that result in the mapping diagram and finding the number 3. How does this connect to our original algebra? Well, when we trace back from the number 8 to the number 15, we're reversing the process of subtracting 7. We're adding 7. To get back to m of x, we added 7. And that's exactly what happened in our solution here. So in this first step, adding the 7 really was taking the number 8 and heading back, finding its source at 15. That is m of x. And we want to know, when is m of x equal to 15? So we go back from that 15 and divide by 5, because that is what will undo the multiplication by 5. And so we found, looking on the diagram, that this part of the equation really represents following the arrow back from the value of mx equals 15, following that back to the number 3. And so we have now a visual explanation of what was going on in our algebraic treatment of solving the equation 5x minus 7 equals 8. What we did is recognize that 5x minus 7 was a function composed of two functions. First multiply by 5, then subtract 7. To find out when that would give us a result of 8, we traced back, first undoing the subtraction of 7 by adding 7. That gives us the number 15. And then we trace back from 15 to the number 3 by dividing by 5, which is reverses the process of multiplication by 5 that originally got us to the 15. And so we visualize solving 5x minus 7 equals 8 by starting at 8, going back by adding 7 to the number m of x, and then dividing by 5 to go back to the number 3, the source of the original 8.